Recording in progress.
Yeah, comes on everyone. Let's start off. Hope everyone has gone through the notes. Last thing that we did, we took a cylinder with a cavity and then we are trying to find the heat flow. So, great. Let's see something similar. Let's say we have a solid sphere with a cavity. So the inside the temperature is 2 T naught. Outside the temperature is T naught. The inner radius is A. Outer radius is 2A. And we have thermal conductivity K is equal to K naught X, where X lies between 2A to A. Matlab, your thermal conductivity is also not constant. It is changing with X. As you go out, it is increasing. So this is a solid sphere with a cavity. Inner surface and the outer surface are at temperatures T naught, 2 T naught and T naught. Faster. Find R thermal. Find the thermal resistance of this system. Find the heat flow dQ by dt. Find dt by dx. Find temperature as function of x. How does the temperature vary with x? X is the distance from the center. Let's get this. Cams on everyone. If you see this and the previous one has similarities, right? In the previous one, the cylinder area was changing. Here also the area is changing. You know the process. We take a small element and then we find the resistance of that small element and then we integrate it. Try. I'll give you 3 minutes. It's a good one. This is how they'll frame an advanced question. Maybe a more than one choice question. How do you choose an element? Everyone should try. I don't know why you guys are waiting for me to say something. Solve. You got 3 minutes. Why are you guys staring here and there? Should revise your notes and come. If you don't revise, this is what will happen. You will keep thinking, oh, what is this? What is happening? Hmm, 3 by 32. Okay. You got a square or a cube, right, Samyak?
I got a square.
Okay, let's see. So, what is the first thing? So, in that sphere, right, we take a very thin element. Why? Because what will you take area as? Every element has a different area. And so, if you take a thin element of radius x and thickness dx, right? So, heat is flowing across this. This is the heat flow. So, resistance of this thin shell will be the length of this shell, which is dx. Remember the formula L by K. L is the length along the heat flow by K into the area, which is 4 pi x square. But what is K? K itself is changing, which is K naught x. That is D naught by 4 pi K naught x cube. Yeah, it's a square only, right? And since all these are in series, so R thermal will be integral dx 4 pi K naught x cube. Limits will go from 2a to a to a to a. That would be 1 by 4 pi K naught. This would be x power minus 3 plus 1 by minus 3 plus 1. 8 pi K naught. That would be 1 by x square. So 1 by 4a square by 1 by a square. That is 3 by 4a square. So that is 3 by 32 pi K naught a square. Check. This is your thermal resistance. What is the heat flow? Temperature difference by thermal resistance. Once you got R thermal, everything will fall in place. This is T naught by R thermal. Great. How do you find the temperature? That would be the good one. So now how did you find the temperature as function of x? Isn't this what we did in the last thing also? There the area was 2 pi xl, yeah? In the hollow thing, here the area was 2 pi xl. If you see, the idea was exactly same. So you did nothing new, but yeah, the area changed. How will you get the temperature? Think, take a minute. Okay, let's see. So what is the temperature gradient? So dq by dt. So when you take this small element, right? The heat that is flowing out is dq by dt. Now remember, the heat flowing from inside to outside is same throughout the every shell. It is the same thing because all of them are in series. So dq by dt is equal to minus ka dt by dx. Now dq by dt we already calculated. We know the value, which is 32 pi k naught t naught a square by 3. And what is k? K is nothing but k naught x. What is area? 4 pi x square. And this is dt by dx. So k naught will cancel. 4 pi will cancel. So you end up with dt by dx will be minus 8 t naught a square by 3x cube. There. If they ask you what is the temperature gradient, this is the temperature gradient. You're done, right? If you got this, then just send dx that side. So what you do is you take a small element and then you write the dq by dt for that small element instead of for the full sphere. And this would be 3 and this would be dx by x cube integral. So if you take x is equal to a, limits, remember, limits are going from a to a, not 0. The temperature here is 2t naught. Here the temperatures, I'll put t subscript x and this is x. So this is tx minus 2t naught is equal to minus 8t naught a square by 3. That is again x power minus 3 by 1 by minus 2. So minus half 1 by x square by 1 by a square. Yeah, you can simplify this. Solve this and you'll get tx ka answer. I'll leave it to you. Clear with the steps? So it doesn't matter what shape I give you. I give you a cylinder, I give you a solid sphere. This is the idea. Always you could take a small element, right? You find the resistance. From there you get R thermal. And then for that small element, you can write dq by dt separately, the differential form, and then substitute dq by dt and finish it off. Have a look at this. You should definitely try this again on your own, maybe tomorrow, right? Just take a rough paper, see the question and try to do. Then you will remember. Right now you might feel like, okay, I understood, but trust me, nothing has gone into the head. You understood, that's it. If I give the same question next week exam, you won't be able to solve. Clear with this? Now, they can have different variations, isn't it? K might be constant, K might change with something else. Any doubts on this? All clear? Clear, na, Vedika? हो गया? Advait? Advait? Is there? Okay. Let's see one more. I hope you remember this question. The frustum or the truncated cone. Here the temperature is 2T naught, here the temperature is T naught, and this length is L. The radius is A and this radius is B. The thermal conductivity is K. And the length is much, much greater than B minus A. Find R thermal. You guys remember this question where we did? Elasticity. And there I told you the shortcut also, how to remember the result. Anyone remember the result?
Yes, sir.
You can type the result. This will come in 3 chapters: elasticity, heat transfer, and current electricity. Yeah, you just have to replace area ka term with pi AB.
Area of
Wherever there's an area term, replace with pi AB. Remember that? But let's get this, because exam mein kya hoga pata hai? They will say k is equal to k naught x, where x is the horizontal distance. Then you're done. You can't use that formula. So you should know how to integrate. Take a minute or two. Try to derive. Let's see how will you derive. The derivation is exactly same derivation what we did in elasticity. And in case you forgot, I'll give a help you see. Step 1, find the radius r as function of x. Start from there. What is r as function of x? Then you take a thin disk. Then you find the distance of the thin disk and then you integrate them. That is how you do this. Try. I'll give 2-3 minutes. So as your x is increasing, you should figure out how the radius changes. Okay, let's see. Do you guys figure out minus the square dot by x? What is even that? So in case you guys forgot, I'll just copy paste it from here. There, this was the thing. This is what I keep telling you. Physics may you will notice this. Whatever you learn in some other chapter will keep popping up. That is the reason physics is easy to learn, and that is the reason physics is also hard to learn. If you're thorough with your concepts and you're doing things properly and you're doing enough work, physics actually becomes easy as you go ahead because you're not really doing anything new. But if you don't revise properly and if you don't solve enough questions, everything will feel like overwhelming. Till now, if you think about this, we got so many concepts, which repeated in multiple chapters. Projected area, it came in 3-4 chapters already, right? This one, you can see these things will just keep popping up. So there, this is how you find the radius as function of x, and then we do dx. Then what we do, we take a thin element. And if you remember here, we did that also, I guess. There we took a thin element here, if you remember. And then we said this. So for this thing, the distance dr will be the length along the heat flow. Remember, the heat is flowing from left to right. So that would be dx by L by KA, and this is pi r square. So this was the reason we needed dx from here. So dx will be L by B minus A K into pi d small r by r square. You're done. So integrate this. You'll get r thermal is equal to L by pi K B minus A integral dr by r square. Limits will go from A to B. Solve this. You'll end up with L by K pi AB. Should definitely remember this is a mains level equation, not the integration. The result is a mains level equation. It has been popped up multiple times. So this question, right, they just give this question. Even you'll see this question in CET kind of exams because they'll expect you to remember the result. Wherever you see area ka term, put pi AB. So the only thing you have to be careful here in advance, how they can frame this, they'll play with that L. So if L is comparable to B minus A, right? So the figure which I'm drawing is actually wrong. The heat flow will actually go like this. So if the heat is flowing like this, then this area pi r square is not perpendicular. You can't solve this problem if L is comparable to A. So when you took L is much, much greater than B minus A, this thing, right, actually looks like a cylinder only. It is so small, you can't even tell the difference. There, so we are talking something like this. So this is B minus A, almost negligible. So we are solving for actually this diagram. Clear with this? So this is one problem in this model. In all the three chapters, elasticity may also do the same thing. There A is the area perpendicular to the cross-sectional area, and T is the tension perpendicular to that area. So clear with this? If your A and B are big, you can't do this problem. So this will be asked in a advancement more than one chess question like that. So the answer is L by K pi AB for all lengths. It's valid for only L much, much greater than B minus A. So they will frame questions of that sort. All clear with this? Any doubts on this? Shreyan, clear with this? Trishi? Clear? Devanshi? Ovia? Ovia, there? Clear? Next thing. Other scams on. You guys said 3, 4, 5 minutes for dinner. I said okay, and now you guys are misusing it. So we have a container insulated. It is filled with liquid, mass m, specific heat S, and temperature is 2 T naught. Now what you did, you connected a rod here. Length L, thermal conductivity K, and area of cross section A. And this right end here is maintained at T naught temperature. So now what will happen? Because the liquid is hotter than the outside, the heat will flow through the rod. If the heat flows through the rod, the liquid will cool down. If the liquid cools down, the temperature will change. If the temperature changes, the heat flow will change. So find the temperature of the liquid as function of time t. So we have an insulated container with some liquid at temperature 2 T naught. You connected a rod from inside to outside. And the other end of the rod, you're maintaining at a lower temperature T naught. So the heat starts flowing from the container to outside through the rod. Find the temperature of the liquid as function of time t. The liquid in an insulated container is in contact with a rod. The other end is maintained at T naught. So assume there is no other heat flow through radiation and everything. It's only conduction. So every time you remove heat from inside, the temperature changes. So then dq by dt will keep changing. So you have to integrate this. That much you must have figured out. Try. This question, right, you can even do better by putting two containers and saying this will decrease and this will increase, and you can play around. Idea is the same. Remember where we did something like this recently? Anyone remember? Thermodynamics. Remember this question? Heat engines. Heat is flowing from one container to another container. Similar idea though. Let's see. Try. Near area. Just look at your answer, okay? If you put T0, what should be the temperature? 2T naught. After a long time, when T infinity, what will happen to the temperature of the liquid? T naught. But look at your equation, what you got. Temperature is becoming negative. Meaning if you wait for enough time, you'll create a liquid with a temperature less than 0 Kelvin. You are the pioneer of thermal technology. Like, you have created a system with a negative temperature, negative Kelvin.
Thank you, sir.
We need people like you in our universe to progress ahead. So aliens will come and fight for us. They'll give you job offers. Happens all the time. Advai, any ideas? I think you need to stop playing with your hair, Ray. So when you keep playing with your hair, right, half your energy goes playing with that only. So focus on solving. Because I keep seeing you, na, after class, you just keep twirling your hair like वो होता है ना पंजाब में सरदार का वो mustache को they keep twirling. You keep twirling your hair like this. So ठीक है, it is fine. But yeah, solve. Try something. T is equal to plus T e power minus. You will get e power. Exponential में आएगा answer. Samyak got T. Samyak, again, look at your answer. If I put T infinity, shouldn't you get T naught? You forgot a minus sign. E power minus आएगा वो. See. So one thing is
सर
clear.
अब
So
से
as the
क्या
time changes, I don't know. Let's see. Your time's up. हो सकता है. So after time t, let the temperature be T. Then in a small time dt, let dq heat escape from the liquid. Through the rod. Great. So the temperature here becomes T, and let dq heat flow from here. So first thing, from calorimetry, if you remove dq heat, temperature will change by dt. So dq will be minus ms dt. So be careful with that. Minus because the temperature is decreasing. And then from conduction, we know dq by d time is equal to minus, you can say K A by L, the temperature of the liquid T minus T naught. Normally it is minus of T naught minus T, so I just send the minus inside. There, two equations to unknowns. Take this dq and substitute here. Minus ms, capital dt. Remember, capital T is temperature, small t is time. K A by L T minus T naught. So this will be dt by T minus T naught is equal to minus Ka by MSL dt. And you know how to integrate this. You're done. Once you got till here, it's math after this. Integrate this. When time is 0, temperature is 2T naught. When time is T, temperature is T. This integral is ln T minus T naught. Limits will go from 2T naught to T. Minus Ka time by MSL. This will be ln T minus T naught. Ln 2T minus T naught is T naught. You end up with T naught into 1 plus e power minus Ka T by MSL. If you try to plot a graph, temperature versus time, This is T naught. This is 2T naught. So the graph will keep decreasing. You'll get closer and closer to this line, but you'll never touch the line. That's how the graph would look. To have a look at this integration. All clear with the steps? Calorimetry, conduction. As simple as that. That is how you go ahead. And this is not the first time. You have seen this before. Whenever you have to integrate, you always start like this. After time t, let the temperature be T and let you remove dq heat and the temperature change by dt. That's how you always start the story. Got this? Any doubts on this? So these are some good problems, all based on integration. So this is the kind of problems you should solve. I won't say they're easy, but they're not tough also. If you just see them like 4 or 5 models, and if you practice some 10, 15 problems, you'll get the hang of it. I can make that question even better by putting a container on the other side also. So then the question would be something like this. You are removing dq heat here. Then this will be dq is equal to minus ms dt1, and this heat is gaining. So dq will be ms dt2, and dq by dt will be ka t1 minus t2 by l. So you have to get dt1, dt2 and substitute here, and then you have to solve. So it's a little more math, but the idea is the same. That would have been a better one, but yeah. And the next one. We have a lake here. And let's say winter, suddenly the temperature outside, right? It started dropping to minus 10 degrees. So the temperature drops to minus 10 degrees. In the atmosphere. And due to this, ice starts forming on the surface. And we know ice is lighter than the water, so it starts floating on the surface. So ice forms on the surface, right? And it floats there. Ice forms on the surface and it starts growing in thickness with time. So it actually becomes like a barricade. Suppose if ice was actually denser than water, ice would have sank to the bottom of the lake, and the ice would have, the lake would have frozen from the bottom. So after some time, the picture would look like this. So we would have an ice block. And we have water here. Right, so we will assume the water is at 0 degree. So the water is 0 degree, outside is minus 10 degree. So what will happen? The heat will start flowing from the water to atmosphere through the ice slab. X is the thickness of the ice slab. The conductivity of ice, K ice is K. And conductivity of ice is K, and then we know LF, latent heat of fusion, density of ice is rho ice, so you know values. So find the thickness of the ice as function of time t. Assume initially there is no ice. I hope the story is clear. You got a big lake, area not given. There's a lot of water at 0 degrees. When the atmosphere suddenly becomes minus 10, the top layer starts freezing. You get a thin layer of ice in the beginning. Then the heat goes through the ice and you start getting more and more ice. So this ice slab is continuously growing. It's becoming thicker and thicker. Find the thickness of the ice as function of time t. So we are taking a case, but in reality, something else also happens. But first, let's find this. Then I'll show you what exactly happens. Everyone should think, give it a try. It's completely fine if you don't get a question. But in the 2-3 minutes, I want you to figure out at least 1 or 2 steps. Okay, this is what is happening. Okay, this is what should have been done. So I'm giving you time to think about it. ऐसा कुछ आएगा यार. Let's see. I don't remember the answer. Try others. I'll give you a minute or two. Let's see. Again, same story. Let the thickness of ice be x after time t. So we got a thick ice slab at thickness x. In time dt, if you guys notice something, right? Whenever I do a problem, if you see, I keep these things constant. How to start a problem. This is the process every time. It doesn't matter which chapter it is. Did you observe this? I do the same thing every time in every chapter. So these are the kind of things you should learn. You're getting it. These things come with practice, and I'm trying to show you that. Because once you get the hang of this thing, right, exam you will be solving problems, on autopilot mode. There is an integration involved. You know what to do. After, always start the problem from the intermediate stage. You don't start in the beginning. Don't start at the ending. So tomorrow, if I ask you current flowing, you'll say the same thing. After time t, let the current be I, and let in time dt, let this much current flow. So this is the thing every time. That is what you do. So in time dt, let dq heat flow through the ice slab. And let dx extra thickness of ice form. So because the heat went away, ice will form. Let dx thickness increase. So from here, dq heat flowed out. Because of this dq heat which went away, the water froze and you got an extra thickness dx. Clear? So first thing from calorimetry. If you think about this, the dq, right, came only in 3 different chapters so far: calorimetry, thermodynamics, and heat transfer. And we're talking about heat transfer, so wo to aayega hi. It's conductivity and L is given. So what is this? So the heat dq which flowed out, where did this come from? This heat has come from the water which is there and water flow. So dq will be the mass of the ice which is formed into latent heat of fusion. What is the mass of the ice? Density of ice, area of the ice slab, area I don't know, so let it be A, and the thickness is dx. Is that making sense? M into LF. So if you remove dq heat, then this much ice will form. Yeah, I think most of you did get it. Let's see. Great. And then from conduction, dq by dt is equal to Ka. The temperature difference is 0 of minus 10 by x. So here the catch is the x is changing continuous. The slab is becoming thicker and thicker. What is dq? I'll just put rho ice area LF dx by dt is equal to K area by x into 10. So area cancels off. You're done. So this will be x dx is equal to 10K by rho LF dt. Integrate this. So you get x square by 2 is equal to 10KT by rho LF. So if you can clearly see here, this x square is proportional to, or you can say the time is proportional to thickness. Clear with this? Meaning it actually becomes more and more difficult to form ice. Do have a look at the integration, look at the steps. Clear with this? So what is the question and means on this question? Huh? Find the ratio of time taken to form the first meter, the second meter, thickness of ice slab. I hope you guys remember it's not 1 meter, 2 meter. First meter, second meter. Meaning this is 0 to 1. Second meter is 1 meter to 2 meters. Get the ratio. That was the main question. Right, Upsa. This is the formula, right? T is proportional to x square. You have seen this in kinematics. A particle is dropped from a building, find the ratio of time taken to travel first meter, second meter, third meter. Clear? Let's see. So T is proportional to x square. So just write this thing as T is equal to some constant x square. So when you go from 0 to 1 meter, this will be C into 1 square. When you go from 0 to 2 meters, this will be 0 into 2 square. So if you want to go from 1 to 2, just subtract them. C into 2 square minus C into 1 square. That will be 3C square. So if you actually see 1 meter, 2 meter, 3 meter, you'll get 1, 3, 5, 7, 9 odd numbers. So the time taken for the first meter is to time taken for the second meter is 1 is to 3. If you take third meter, it is 5. Fourth meter is 7 and so on. So you can see actually as time passes, it becomes more and more difficult for ice to form. So the thicker the ice slab, more difficult for the heat to flow. So the slower the ice will form. So one reason why the lakes don't freeze, even during, if you go to Antarctica or Arctic cycle, right? The entire oceans don't freeze, even though the temperature is very low. And there is actually another reason. What actually happens is this. So what actually happens is when the ice starts forming, let's say outside temperature is very low, -10, minus something. So let this thickness be X. So heat is continuously flowing from here, right? Mostly on the surface here, the water will be 0 degrees because you are in contact with the ice. So yeah, before freezing, it will remain at 0 degrees. But tell me one thing, when is the water ka maximum density? At which temperature water has a maximum density? 4 degrees, isn't it? That means the water at the bottom of the ocean is at 4 degrees. So when the temperature drops to 4, it actually sinks to the bottom. So there's a temperature gradient, right? Is 4 degrees. Since density is maximum. And who maintains this temperature? The heat from the Earth's core. These volcanoes and that water and everything, right? There is a heat which is going from the Earth's core to the crust. So what is happening? The heat is flowing from the bottom of the ocean to the ice slab, and the heat is flowing from the ice slab to atmosphere, and this thickness will be D minus X. So if more heat escapes outside, ice will become thicker and thicker. If outside temperature starts rising, the heat from the bottom will melt the ice becomes thinner. So at some point you actually reach an equilibrium. So the heat which is going from the bottom to ice will become equal to the heat which is going from the ice to the atmosphere. So at some point you reach a steady state. Whatever heat you're coming from the core, everything escapes. So this formula will be K water area by D minus X. The temperature difference 4 minus 0. This will be K ice A. Temperature difference will be 10 by X. So from here you can calculate X ka value. So this is what actually happens in real life. So that is the reason in Antarctica, right? Even though the temperature is sub-zero for 9-10 months, even during summer, the temperature there is like single digits maximum. So the hottest day in Antarctica would be like a single digit. So technically speaking, the ice should just keep forming. And these people have found out, the ice slabs in Antarctica are almost 2 kilometers thick. And you know how long it takes to form that amount of ice? The estimated time right now we estimated is 5 million years. 5 million years, that is 50 lakh years. So that is how much time it took to form the 2 kilometer thick ice. And we are melting using global warming within a decade. So yeah, I think in a century we'll finish off all the ice. Humans are pros in that. Right? Humans have that capability. Once the human decides, right, that he wants to eat something or destroy something, we will finish it off. And this we have seen in history over and over and over. Meaning one of the famous example, right? There is a pigeon called carrier pigeon. Right? I told you this thing. So this thing during 1800s, right? There is a species of pigeon called carrier pigeon. And these things, right, always move in groups. When I say a group, each group will contain almost, 20 to 30 lakh pigeons in one group. These things are huge groups. And when these groups fly, right, literally the city becomes dark. So the flocks are so big. And I think in 1860s or 50s, the estimated population of these pigeons was more than 8-10 billion. So the pigeons used to be so much, billions. Getting it? And then somewhere in 1870s, right, 1860s, a rumor spread. These pigeons have some, some special qualities. If you eat that pigeon ka meat, you will become young. Right? You will become more beautiful. And you know this thing, right? If you just tell people you're going to become beautiful and young, so people will eat. Nowadays, if you tell people, right, it has a lot of protein, you'll get 6-pack, so people will eat. Yeah, so a rumor spread somewhere, and these people started eating these pigeons and they started killing them right and left. So the rumor spread somewhere in 1870, and the last pigeon got extinct in 1921. So in a span of almost 40, 50 years, we have finished the pigeons. Getting it? We have indiscriminately killed every one of them, and we are done. If I have to give you one more example, right? In Thailand, Thailand or Malaysia or Bali, somewhere, okay, some in that area, right? They had a big problem, rats. These rats, right, were literally eating away and destroying 50% of the country ka grain ka production. 50%, imagine. The entire country, if it produces rice grains, these rats are going into the, the rice granaries, shitting on them, eating them, spoiling them. 50% of the country production is getting wasted. There was literally famines. I don't remember which country, but it is somewhere in that area. I think it is Thailand or something. So the government, right, initially they tried everything, okay? They are like, they had squads, who will go and kill the rats and everything. Nothing worked out. And then they came up with a policy. For every rat that you kill and submit, we will pay you money. That's the best thing, right? People will get some job to do. And overnight, people started becoming rat hunters. People started forming groups. They used to catch rats. And catching rats was so easy. Huh? You just need to go to the street, put your hand down, and you'll find a rat. There were literally so many rats. So it was free money, right? Just think about it. If a 1,000 rupee note or a 500 rupee note is flying on the floor, right, somewhere on a road, people will take it, isn't it? So rats were literally money which are running around. And people started catching rats. And they started submitting and they started getting money, and people were so happy. And people started catching rats. And now the government had a problem. What to do with all these rats that you're catching? Then they brought some scientists, as usual, social media influencers and blah, blah, blah. And they started publicizing. Like, the rat ka meat is very lean meat. It is very good for health. वो इंडिया में ऐड आता है ना, हर रोज एक अंडा खाओ. That दूरदर्शन में ऐड आता था, eat every day one egg, it is good, something. So they started putting a literal promo like, eat a rat every day, you will be healthy, you will get a lot of meat and protein and blah, blah, blah. Initially, people were not that interested, but remember, it's a famine ka time. People were literally dying in villages and all. So they started eating. It was made well, okay? It was prepared well. They started eating. And after a few months, right, people actually started acquiring a taste for the rats. In a year, the rats were gone. They finished all the rats. Thailand has solved the problem by eating the rats. Kidding? Eh? Then they had a new problem. Now, people who got used to eating the rats, now they wanted to eat rats, but rats are not there. They started growing rats. So they have rat farms where they grow rats in a very hygienic way so that you can be made into whatever stuff and feed the people. See? So, we humans are capable, like, you decide, so we don't stop, we finish it off. Anyway, so that is one thing. Yeah, so that's a little bit about conduction. So you saw conduction, right? The main thing is the integration problems. That is the main theme there. The next thing is radiation. So in conduction, especially, you need to see those integration problems. The solid sphere with cavity, cylinder with cavity, the truncated cone. These are the main things. So what is this radiation exactly? Why do we get? Now here we need to go back to a statement. According to classical theory of electromagnetism, an accelerating charged particle emits photon. Do you guys remember where you heard this statement? This is one of the drawback of Rutherford model, gold foil experiment. In that, right, Rutherford says electrons go in around circles like a planetary model. Then the people argue like, if an electron is going in a circle, it has a centripetal acceleration, and an accelerating charged particle emit a photon. And so eventually the electron should collapse into the nucleus and the atom should disappear when it is gone. But it doesn't happen. If you guys remember, this was one of the drawback. You heard this statement first time there in Rutherford model ka drawback. So an accelerating charge, why this happens, that we don't know, but it happens. charged particle emits photons, right? So there's a name for this thing. They also call it as breaking radiation or Bremsstrahlung radiation, which is the name of a German scientist. But yeah, we'll not write it. We'll write that in modern physics. So now if you take any body with a temperature greater than 0 Kelvin, the molecules are vibrating. Now, when you say a molecule, remember the nucleus is a positive charged, concentrated positive charge. So when it is oscillating, it is going front to back means it is slowing down, it is speeding up. It is slowing down, it is speeding up. So that means they should emit photons. That means right now, even you are emitting photons. Maybe they're in the infrared region. That's why we can't see. Means if you take a body of temperature minus 100 degrees and put it in a room of 1000 degrees, even then it emits photons. It will absorb more, but it is still emitting photons. So it only depends on the temperature of the body. The molecules are in a state of constant vibration. Did you guys ever hear this word background radiation? So there is a thing like that, the Big Bang theory, right? It says initially when the universe started, the temperature was 10 power 34 Kelvin. So everything was like a point, and then when it exploded, it started cooling down, cooling down, cooling down. I think currently, when it cooled down, that you can say it's like an average temperature of the universe. It's like some 4 Kelvin right now, even lesser than that, something of that sort. Now, like I said, so because of this, right, there is a constant emission everywhere happening in the universe. So a guy got a Nobel Prize for this. Arya, bolo.
So can we find the wavelength of the photon emitted?
They're too small, but they do exist.
Okay,
The
sir.
background radiation ka bol rahe ho, or any photon?
No, sir. Like when the photons excite and de-excite that way.
This thing we have later on, we will see. We can't find
Electrons.
exactly how much, but we can find approximate average.
The average only we can find, right?
Average only. Exactly, you can't tell how much which photon will come. It's completely random. Right, and this thing somewhere, it happened in 1980s actually. So these people, right, were working on radars. So they had this big observatory, right, and they were working on it. So they're putting it, towards the space, and they're trying to get some readings. And these devices are so sensitive, right? If you just put a washing machine like 100 meters far, it will detect washing machine vibrations also. Getting it? So it's a very sensitive device. So that is the reason if you see these observatories, right, they're placed on top of a mountain, isolated area, very far, far, far. So these things are placed like this. So, and this thing, right, started giving some weird readings, and this guy didn't understand. So they went into this. It is a big one. You can literally walk inside, and they found out there is a pigeon ka nest. They cleared it up. They cleaned it. These pigeons have no work, right? So that is one thing. And then they cleaned it up everything, and then they came back and they still found that same weird reading coming up, and they didn't understand. I thought maybe someone is, maybe signal is coming from somewhere. And they kept on trying, putting this dish in every direction. And the interesting part, they found out it is the same, that radiation coming in every direction. And when they talk to other researchers in different parts of the world, everyone observed the same radiation everywhere. And right now we know this radiation is coming, it is everywhere in the universe, right? And that is one way we proved actually that, universe is expanding. We can prove it. Baad mein dekhte exactly what is that. So, and they got a Nobel Prize for that. So, yeah. You should. The word is background radiation. Someone wants to read more, you can check it out. So if you have more temperature, you vibrate more faster, and when they vibrate or collide, understand, even though the molecule is neutral, in reality, the charges are not exactly matching. So the nucleus is a concentrated positive charge and the electrons are moving around. So yeah. Yeah, cosmic microwave background radiation. That's your full name. So vibrate or collide, they accelerate or decelerate once the photons are emitted. So this process is called radiation. So this phenomena of emitting photons is called radiation. So in radiation, right, there is no transfer of material or you don't require medium to propagate. We get the energy from sun to earth, 15 crore kilometers. There is no medium in the middle. And photons don't have any mass. There is no transfer of matter and does not require medium to propagate. That's a bit about it. Take a break, come back by 9:40. We'll continue from here. Chalo, hands on everyone. So let's say if you take a body there and let's say it is at some temperature T. So this thing emits photons of different wavelengths. We will see that what kind of wavelengths also will come out. Now a bit about this. You studied this in chemistry. Cams on everyone. So energy of a photon E is equal to hc by lambda or h into frequency. You know this stuff. H is your Planck's constant. C is the speed of light. Lambda is your wavelength. F is the frequency. And you can, so this is one important formula here. And you know from de Broglie wavelength, so these photons, right, even though they're massless, they have momentum. So the momentum of a photon is given by h by lambda. And from here, we can actually figure out something. So if you take intensity is nothing but the power by area. Power is energy by time. So this is area in which the power propagates. Right? So power is nothing but energy by time. So that is the number of photons per second into energy of each photon. This will be n, and energy of the photon is hc by lambda, or you can write hf. So if you substitute here, this will be number of photons per second. H frequency by area. So there, so intensity is proportional to number of photons into frequency. We will use this in photoelectric effect later on, but yeah, just have an idea about this. Clear with this? We're going to do a problem on this later on, you will see. So this is a bit about photons. I'm sure you know this thing. The hc by lambda and h by lambda. Next thing, coefficient of absorption. Now, when you take a body there, when radiation is incident on a surface, three things can happen. Let's say this is an incident radiation. One, you can reflect. Second, you can get absorbed. Third, you can get transmitted. Which you also call as refraction and all that stuff. So that is all transmission only. So whenever you shine light on a surface, these three things can happen. Right? Others comes on. So the total energy, Q total, will be Q reflection, Q absorption, and Q transmission. If you divide this thing, Q absorption by Q total, Q reflection by Q total, Q transmission by Q total, that ratio is 1. So this is written as A plus R plus T. So this each term, right? So this is A is called the coefficient of absorption. So A ka value will tell you how much the body will completely absorb. So if A is equal to 1, it's called a black body. We'll talk about that in the next page. That means if we have a black body, then whatever falls on it, everything will get absorbed. Then R is Q reflection. By Q total. What if R is equal to 1? There is no transmission, there is no absorption. It's a perfect reflector. It's a perfect mirror. Everything that falls on it, everything will get reflected. T is transmission by total. What if T is equal to 1? It's a transparent material. Think of air. Whatever light that passes through the atmosphere, most of it comes to you. It doesn't get absorbed, doesn't get reflected. So you can think of air is like transparent. Clear with this? Then so what is this black body exactly? So let's talk about that black body a bit. So basically in a black body, absorbs all the radiation that is incident on the surface. Now, when you say black body, right, most people think about a black hole. So don't think about a black hole. Right? A black body can have its own emission. So there's only one definition. Whatever falls on you, absorb everything. A black body need not be black and it need not be a body. That's an interesting definition there. A black body need not be black. It need not be a body. Example, sun is actually close to a black body. Again, like I said, don't get confused. Black body tells you only one thing. Whatever falls on it, will not get reflected. Everything will get absorbed. Getting it? Sun does not reflect anything. Sun will absorb that energy. It will make its own energy. Then it will emit its own photons. I hope you're getting the difference between reflection and emission. Moon is a reflector, isn't it? Moon does not have its own light. It reflects the sun light. So a black body, right, is simply absorbs everything that falls on it. So you can still see a black body. The sun is close to a black body. It can have its own emission, right? The second thing, this is called Ferri's black body. This you should know. Where are you? Heat transfer. If you're in board exams, right, they would ask you this. Explain black body and define Ferri's black body. So this is the picture there. This is called Ferri's black body. So how does this work basically? So basically you have a double, I'll just draw one more picture here. Have a small hole there. So the idea here is whatever light ray that you send into this hole will just keep on bouncing inside and it will never come out. It will get absorbed eventually, right? So here the hole behaves like a black body. The body is not the black body. Just think about this. Whatever light that falls into the hole will never come back, isn't it? So here the hole behaves like a black body. That's why I said it need not be a body. And these black bodies, right, behave little, meaning they look little different. So just think about it. This thing, right, black body, right, it just absorbs everything that falls on it. So imagine if you have a material like a black body, right, and if you paint your whole room, what do you think will happen? Let's see how it would look. This is a good one. Huh? So currently, right, the material which is the black closest to the black body, right, we have something called Venta Black 2. So if you ever heard about that material, Venta Black 1 was the previous one. Now Venta Black 2 is there. These are actually made of carbon nanofibers. So this carbon nanofibers, right, it's like small, cylinders. So when the light falls into the cylinder, it just keeps bouncing inside. So the light does not come out. The light just goes inside the cylinder. So they completely absorb the light. So Venta Black 2, right, absorbs almost 99.997% of light. I think Venta Black 1 was 99.95 something. So, but these are very expensive materials. So what we have something close to that, right, is called Muso Black. So Muso Black is a little cheaper. It absorbs almost 99.102%. But yeah, I think for all purposes, that thing works well. And when we say black, right, people have this misconception. You think your hair is black. Even in blacks, you have shades. You just don't realize how black can be. Look at this.
Muso Black. It absorbs over 99.2% of visible light. So I'm going to be painting some stuff with Muso.
So he has that bottle. It's a Muso Black Cup paint. Last time I checked it, you'll get it in Amazon. But India mein nahi hai. You have to get it from Amazon US. I think it was 6,000 or 7,000, that small dabba. So yeah.
So Black and comparing it to Black 3.0. And
if you see Batman ka vehicle, right, it must have been painted with something like this.
So Black. And putting a light bulb in, that would take a room.
So he's taking the Muso Black and he's painting an apple. See how it looks.
Don't become black. That is so 3.0.
This is not black. You can see it is still
like
glossy and shining. It's reflecting light.
because it's still wet. So it's glossy a little bit, but let's see what it looks like when it dries. Okay, here we
There.
go. Here's an apple painted with Musso black. This is amazing.
Can you see when he turns it? Basically, whatever light is falling on it, everything is getting absorbed. You can't even tell the thickness of the, meaning if you don't know what it was before, you can't even tell what it is. It just looks like a flat surface, isn't it? You can't see the thickness, you can't see the nothing. It just looks like there is a hole in a screen, isn't it?
Look how it just disappeared. You can't even tell what I'm holding. You can't see any contours of it whatsoever. So cool.
There's, if you have put a black background and keep this apple, you can't see the black part. It just looks like it's gone.
That is so cool. Look at this from all angles here. That is the coolest thing
You can
I've
see the
ever
apple.
seen.
Once you go this side, it's nothing. Just looks black.
Okay, this is my favorite thing I've ever painted. This is so cool.
Can you see this thing? You can just see there's a flat surface, isn't it? You can't see the thickness.
Video it.
See how dark it is. Now tell me something, okay? So if I take this paint and if I paint your entire room with Musso black, okay, and you go into the room with a torchlight, what do you see? If you paint the entire room with a Musso black, there are no lights, nothing inside, and you enter the room inside with a torchlight, and you switch on the torchlight. What do you think you will see? Remember, whatever light falls on it will get absorbed. So nothing will reflect back. So you will see nothing actually. You will see there is no wall. You can't even tell what depth is the room. You can't even tell where is the wall. Now imagine this thing, okay? In such a room, if you put a light bulb and if you switch on the light bulb, and if you're standing in that room, you will just see the light bulb, you know, as if there is just one thing in the space. Like you can't see the walls, you can't see anything. So let's see, this guy is going to do that. Not a full room, but a small box.
Other video. But
So-
this is Musso black painted with an airbrush. And you can notice a slight tint.
I'll post this video, you guys can check it out. He will show you actually black has different shades.
And then we're going to put a light bulb inside and see
So
what
there, he
happens.
took a box
What will
and
it
he
look
painted
like
with
on the
Musso
wall?
black. So he's painting the whole thing inside with Musso black.
Okay, so I have my flashlight
Now
on.
think
I'm
about
going
it,
to be
huh?
putting it in the box.
Normally, if you have a room and you go inside with a light, you should see the walls. See what you
I'm
see.
looking what it looks like through a small hole. This is so weird. It looks like I'm shining this outside and that's the moon in the sky or something. It's completely black. It's reminiscent of the night sky.
There,
You can't see
can you
any
see? You can't see any
Contours of the
walls.
box whatsoever.
You can't see anything. See, normally if you put a light in a room, you should see something. You see nothing.
Oh, cool.
That's because nothing is getting reflected.
Okay, the camera is in.
Then he put the camera inside. See what is happening. You can just see that phone ka camera, but look at the surrounding. And the green spot is that, you know, inside the lens, there is a reflection in the camera. You can ignore that.
Inside there with the light bulb. It looks like the moon out a window or something. That is so weird. Hey everyone, thanks for watching another episode of the Action
Okay.
Lab. I hope
So there is this one guy, right, in YouTube channel, man. This guy made a ninja dress. He painted the whole dress with Musso black and he started running in the streets in the night. Right? So what do you think will happen? You just can't see him, right? Like when he's running there, you just see some shadow kind of thing moving there. Even if you shine some torchlight or something, you see nothing. But it can be pretty dangerous, huh? That means a car on a road will not see you. They'll just hit you and go. So that guy did a video like that. He had a black screen. He painted his whole dress with Musso black and is standing in front of it. You can't see him. It's complete. It just got mixed in. When he opens the eyes, then you can see two eyes on the screen. There is a video like that. I don't have it, but I'll see if I find it. I'll post it on the group. So that you can actually make a ninja dress like that with a Muso black thing. Clear with this? It's just called a black body. It is just a name, Ray. So be careful. Just because it's called black body, it need not be black and everything. Yeah, universe, sky, there is nothing to reflect, in the universe. Most of it is an empty space, isn't it? That is the reason you can't see anything in the sky. Like during night time, why is the sky dark? There's nothing there to reflect. You can see the moon because it is reflecting. So yeah. Anyway, so that's a little about the black body there. Then we have a few more definitions. Spectral energy density. We will talk more about this in the next class. But E lambda. So spectral means wavelength, energy density. So how much energy is coming? Yeah, you can say black hole is a black body. So this is the amount of energy. But again, black holes have a problem. Our physics, whatever we know, will break down once you get close to the black hole. So we'll not get into it. This is the amount of energy emitted per second per unit wavelength. So if you have a body and when it is emitting photons, we know, right, it will not emit only one single wavelength, it will emit all different wavelengths. So E lambda tells you how much is each wavelength contributing to that energy. Let me give you an analogy. Listen to this. Let's say we have 1 rupee coins, 1,001 rupee coins. We have 2 rupee coins, 2,000. We have 5 rupee coins, 5,000. And we have 10 rupee coins, let's say, again, 3,000. So how much money do you have in terms of 1 rupee? 1,000. 2 rupee coins, how much money you have? 4,000, 25,000, and this is 30,000. Clear with this? Now here, look at this. How much money you have? This is the total money you have. That is 30, 60,000. But if I ask you this question, how much money is 2 rupee coins contributing to you? What will you say? The 2 rupee coins are contributing 4,000, isn't it? That is your E lambda. You get in the analogy there? The denomination 1 rupee, 2 rupee, 5 rupee, this is like wavelength. So different wavelengths are like different denominations. The number of coins is like number of photons. This money is like E lambda, how much each denomination is contributing. If I ask you this question, how much money is 5 rupee coins contributing? 25,000. How much money is 1 rupee coins contributing? 1,000. Is that making sense? And the total money you have is the total amount of energy emitted by the body. So spectral energy density is simply the energy emitted by a given wavelength. Is that clear, everyone? So think of it in terms of money. It's like you have different denominations, and each denomination will contribute different amounts of money. I hope the analogy is making sense. Right? So, but anyway, we will talk about this again later on. Then we have something called emissive power. This is the amount of energy emitted per second per unit area. The form of radiation. So emissive power is nothing but intensity only. Kirchhoff's law of radiation. So this thing says at a given temperature, the ratio of spectral emissive power. That's your E lambda to spectral absorptive power. So spectral absorptive power is how much energy are you absorbing for a given wavelength. So the moment you see the word spectral, they're talking about wavelength. Is constant. But anyway, what does this mean in simple words? So this thing says E lambda by A lambda is constant. So E lambda is proportional to A lambda. Just try to understand the meaning of this. The body which can absorb more can also emit more. E tells you how much are you emitting. A tells you how much you are absorbing. So indirectly what is being told is, if you are a good absorber, you should also be a good emitter. If you are a bad absorber, then you're also a bad emitter, vice versa. So Kirchhoff's law of radiation simply tells you a good absorber is also a good emitter. But just think about this. Let's say you have a body which is a good absorber but a bad emitter. What do you think will happen? You will keep absorbing more and more, but you will emit less and less. So your temperature of the body will keep on rising. Clear with this? Yeah, let's see a theoretical question on this. You took a black body and a normal body. Of same dimensions. Are placed in a hot furnace. Who looks more bright after a few seconds? After a few hours. Then question is not over. Then they're removed from the furnace. And placed in a cold, dark room. Again, same question. Who looks bright? After a few seconds and after a long time, or after a few hours. What do you guys think? What do you think will happen here? Remember, initially both are at low temperature. You kept them in a hot furnace. Tell me one thing. When do you think something is bright? When it emits light, right? If something, you're getting more light from a body, you think it is bright. So if you put a black body and a normal body in a hot room, initially both are cold. Who absorbs more heat? The black body. And if you absorb a lot of light from the surrounding, then the surrounding will look dim. So see. So you kept a black body. You kept a normal body. Now the black body absorbs a lot of heat. Remember, you still didn't reach steady state. Huh? You're still cold. The furnace is pretty hot. The normal body is also absorbing, but it is absorbing less because a black body is a good emitter and also it's a very good absorber. So black body absorbs heat at a faster rate. So maybe the black body is absorbing 1000 calories per second and the normal body is absorbing 200 calories per second. And if you absorb all the light from the surrounding, right, therefore the surrounding will start looking dim. Think of this way. Why do you think it looks bright? Because you're getting light from the furnace. And if you start absorbing light in that particular area, that area will look dull. Ever heard about this thing, sunspots? If you look at the sun pictures, right, you will actually find there are black spots on the sun. So these black spots are actually, due to the high magnetic field, the temperature of this spots is around 1000 degrees less than the surrounding. It is still hot, that is still 5000 degrees. But it is a little less than the surrounding. So these spots start looking dark. You're getting it? So if I put a light behind you and make you stand in front of it, and if the light is coming from the back, you will look dark. So surrounding becomes dim. So the normal body will look bright for a few seconds. But if you keep it for a long time, they both will look same because you reach steady state. The black body is absorbing more, but it is also emitting the same amount. That's like the black body is absorbing 1000, emitting 1000. Normal body is absorbing 200, it also emits 200. So you can't tell the difference. You can't even see the bodies actually. They will mix up with the background. Everything will look like normal. They reach steady state. Whatever you're absorbing from the surrounding, you're emitting. So you can't tell the difference. Then what you did, you took them and kept them in a dark room. Now remember, the black body got heated up. So it is emitting now. It's emitting more compared to this thing. So the black body will look bright. After a long time, both will cool down. Again, they will look the same. Is that making sense? If you absorb a lot of light from the surrounding, the whole surrounding will become dim. Let me show you something, how it would look. There, we have a movie there. Black body radiation starring iron ball and brick chunk. So we don't really have a big furnace. So if you're in a metallurgical lab, you have the small kind of furnaces. You can see, you can take the temperature up to 1000 degrees. So there we have a metal ball and a brick chunk. Can you guys tell me which one is close to a black body? Which one is close to a black body? Metals are good reflectors, isn't it? Metals reflect light. It's a good reflector. Black body will absorb everything. So the brick is close to a black body. Getting it? Metals absorb, metals reflect. So yeah. Don't get confused with conduction. Metal is more conducting than brick chunk. We are talking about radiation here. Anyway, so there, look at the furnace there. Just look at the furnace. This is 1000 degrees. This is how it looks. Can you see the background? You can't see what is behind, right? You can't see the background. But see what happens when you keep them inside. Notice this. You can't see the background, okay? I'll come back to a second to show you. He's taking both of them and he's keeping them inside. Did you notice something? The moment he kept it, you can see the background now. Observe किया, देख see. This is before keeping. Can you see the background? It's not clear. This is after keeping. Can you see the background? You can see little. Why? It is absorbing light, so surrounding became dim. It's going to put the brick chunk. Now you can see the background even more clear because both are absorbing. He left them inside for some time, 30 minutes. Now, what do you think will happen? They both have reached steady state. Whatever they're absorbing, they're emitting. That means you can't tell the difference between the brick and the background. See how it looks. Can you see? I know there's a small thing, but can you see the picture there? They got mixed up with the background. This is what I was saying. Because the furnace ka temperature is 1000, body ka temperature is 1000, they're emitting and absorbing same. So you can't tell the difference who is the furnace and who is the body. Yeah, you can see the still contour, but you can clearly see the difference between the first and the second picture. He will show you see the comparison. That was initial. This is after long time. Can you see the difference? So initially both are absorbing heat, the surrounding became dim. That's the reason you can see the bottom and you can see the back part of the furnace. But after a long time, everything remains same. Now they're going to take it out and put it outside, which will cool down faster. The black body, right? The brick will cool down faster. There he's taking it out and is keeping it out. The first thing he took out a metal ball. It's hot. You can see how fast it is cooling down. Color is changing. This is a brick chunk. Huh? Now see, the brick chunk came second, okay? But see how fast it cools down. See, the ball is still bright. There it became almost dark. It's still hot, but yeah. There, the black body is close. The brick is close to a black body compared to the metal ball. You leave it there for a long time, both will become dark. I hope you're getting the idea there. Arya.
Like, how do they reach such temperatures inside the wall?
You can reach it, right? The surrounding material you have to make sure 1000 degrees is not really that great, right? Iron ka melting point is around 1400 degrees. So the metal which you're using is something else. It's not iron or something. They use alloys which have a much higher temperature of 1800 2000 degrees.
Okay, sir. Sir, also
Why all
when
that? When you switch on your stove, right? Your stove mein the gas ka flame aata hai na, the temperature is only 1000 degrees. Didn't you learn that it's in chemistry? Oxyacetylene flame, oxy something flame. The blue flame, when you see the blue color flame, it is very hot. It reaches temperature of 3000 degrees. Why all that? Switch on your light bulb. पता है ना वो पुराना incandescent bulbs. That filament has a temperature of 4000 degrees. So there,
Sir.
it can be created. Huh.
also, like, why can't it happen so key that iron ball will expand and the area increases? Therefore,
Hey, alpha is very small, right?
something
इतना
like
मत
that.
सोच तो. Alpha बहुत छोटा है. Those
Okay.
expansions and all are almost negligible. All clear with this? Param, clear so far?
Yes, sir.
Great. Next thing, Stephen's law. So let's do a bit of a theory. Next class we'll do more problems. So what Stephen law says is if you have a body, temperature TB, it's emitting photons, dq by dt, I'll put a small subscript here, emission. So the heat emitted is given by minus sigma A E T body power 4. So how much energy the body emits in the form of radiation depends only on the temperature of the body. So this is nothing but the heat per second emitted in the form of radiation.
So if you write emission, then I don't think we need the minus sign.
It is just to show that the body is losing heat, na? Or else if I write dq by dt, it's confusing. So just to put an E symbol there, nothing much. So the negative sign indicates the body is losing energy. Sigma is called Stephen's constant. It's very easy to remember the value of this. 5.67 into 10 power minus 8, 5678. That is how I remembered. So watt units are important. Huh? They'll ask this thing in units and dimensions. Watt per meter square Kelvin, power 4. TB is the temperature of the body in Kelvin. E is the coefficient of emissivity. It's not coefficient of restitution, be careful. So this is a dimensionless quantity. And E ka value lies between 1 to 0. So E is equal to 1 for black body. So E tells you how good a body is a emitter. So a black body is a perfect emitter and a perfect absorber, right? And if you take E is equal to 0, meaning there is no emission, it does not emit any light of its own. So, and if you notice something here, the radiation emitted does not depend on the surrounding temperature. So how much radiation you emit does not depend on what is the surrounding temperature. So if you take a body at 10 degrees and put it in a room of 30 degrees or 3000 degrees, it emits the same amount of radiation. Then we have something called Prevost theory of heat exchange. This thing says if you take a body and if you put it in a surrounding temperature, now you'll absorb energy from the surrounding. Now how much energy you absorb will again depend on the surrounding temperature. So dq, I'll just write this as absorption. Because everywhere if I write dq by dt, you'll start getting confused which is dq by dt. Plus sigma A E T surrounding power 4. So interestingly, the constants and everything are the same, only the temperature changes. And again, if you absorb here, how much you absorb depends only on the surrounding temperature. It doesn't depend on what is your temperature. So this is heat per second absorbed from surrounding. In the form of radiation. Independent of temperature of the body. Yeah, you can say that way. Yeah. Now, if you combine both of them, then we get the net heat flow. So dq by dt will be the combination of both of them, the absorption and the emission, minus sigma A E. So this is the formula you need to remember, okay? TB power 4 minus TS power 4. This is your main formula in radiation. This is your net heat per second. So if TB is greater than TS, that means the body is emitting more heat than absorption. So body will cool down. If TB is less than TS, you're absorbing more than emission. The body ka temperature will rise. Now, there can be a theoretical question. What if they're equal? If TB is equal to TS, will the radiation stop? If TB is equal to TS, the body will still continue to emit photons. So that is one thing people think, like, if the temperature becomes equal, body will stop emitting photons. No, that is wrong. You're still emitting photons, but you're absorbing the same amount of things. So yeah. Yeah, it's called dynamic equilibrium. So body continues to emit photons, but it will absorb the same amount. Your emission doesn't stop. You can put on the formula there. It's a straightforward formula there. Just let's say one or two small questions on this formula based, and then we'll go ahead.
So we don't have its proof for syllabus.
Which one?
So the proof for Stephen's law.
There's no proof right here. We don't need it.
Okay.
That is a law. It's like done, experimentally derived. Let's say a simple one. We got a sphere. We got a big sphere. Let's say this temperature is 127 Celsius and this temperature is 327 Celsius. This radius is A. This radius is 2R. This E is equal to 1. This E is equal to half. And the temperature of the surrounding is 27 degrees. Find the ratio of heat per second. If I don't mention anything, it is net heat only. There, it is just formula substitution. So be careful. In conduction, it is a different phenomenon. The formula is different. Here, this is a radiation. Let's get this is just numbers. Done. 16 by 81. Yeah, numbers are not great. So this is, if I'll just put Q1 per second by Q2 per second, sigma is same, area will be 4 pi r square, E ka value is 1. This should be in Kelvin. So this is 400 power 4 minus 300 power 4 by sigma 4 pi 2r whole square. This is half, and this is 600 power 4 minus 300 power 4. 4 pi r square will cancel. This will be half into 4 power 4 minus 3 power 4 by 6 power 4 minus 3 power 4. You can use that a square minus b square ka thing and you can solve. You'll get it. 35 by 486. Yeah, fine. Whatever it is. It's just calculations there. All clear with this? Let's do one more easy one and then we'll wrap up for the day. So we have the sun. And sun is emitting radiation. Temperature of the surface of the sun is 6000 Kelvin. It's almost a black body. E is equal to 1. The radius of the sun is almost 1,000,000 kilometers, 10 power 6. Right? So, and outside surrounding is vacuum. So when you say vacuum, right, you can assume the temperature is 0 Kelvin. Now you need to understand something. Sun is emitting radiation, but where do you get this energy from? So sun emits radiation by converting mass into energy, Einstein mass equivalence equation. Nuclear fusion, basically. Right, through nuclear fusion. Fusion, not fission. Currently, all the reactors we have on the world are fission reactors. We break uranium. So this is something else. So E is equal to mc square. So this is called energy mass equivalence. So the question is, find the mass lost by the sun per second. Let's get this.
Neglect
So how
change
much?
in volume.
वो सब neglect करना. Why are you obsessed about expansion and volume, Ray? Let's get this thing. Hope the question was clear. If you're emitting energy, it should come from somewhere. So the only way that is coming is mass is becoming energy. E is equal to mc square. C is the speed of light. So the question is, how much mass is the sun losing every second? Finish off. Last one for the day. So how do we start this? Numbers are bad. Let's see the thing. So first, let's find out how much energy the sun is releasing every second. That comes from Stephen's law. This radiation dq by dt is sigma a e TB power 4. Vacuum is 0 there. So this is the total energy emitted by the sun. and you're not absorbing anything because there's a vacuum outside. And where do you get this from? This is coming from E is equal to mc square. So this must be from, so when you say E is equal to mc square, so when you do this as energy per second, this will be mass per second. So I'll put both the sides times E square. So this will be sigma A E TB power 4 by C square will be mass per second. Yeah, done. So just substitute the values here. So 5.67 into 10 power minus 8. Area will be 4 pi into, that is 10 power 6 kilometers. So 10 power 9 ka square. E is 1. Temperature is 6000 to the power 4. You might think like, wow, such a big number. You're forgetting there is a big boss sitting here, 3 into 10 power 8 whole square. That will come and kill everything. But still, this is going to be a huge number. I think this will come in the range of around 10 power 8 kgs per second or something. So yeah, that will give you mass per second. You lose a lot of mass every day. I think you might be losing around something like maybe 100 crore kgs every second. It might look huge, but if you compare to the sun ka mass, that is nothing. It's like you losing every day one hair ka strand. So how many days will it take for you to lose your entire hair on the head? So something of that sort. So numbers are bad. So you can check it out. All clear with this? There. So that is a bit about it. So next class, when we catch up, we are going to do some really good ones, right? So we have some really good advanced problems on this. So next class will be quite important. So we'll be doing that. Okay, with that, we'll wrap up for the day. So I'll see you guys again on Tuesday. And I think mostly by next Thursday, we will wrap up the chapter. Most of it will be done, and another 1.5 class. And after that, we'll start off with SHM also. So, okay. So any doubts, anything else, please stay back and ask. Also, you're free to leave. I hope you have given the